Welcome. In this particular session, we will be discussing about different types of crystal imperfections. So the content of this particular topic is, first of all, we will discuss introduction of defects in crystalline solids. Then we will discuss various types of point defects like vacancies and self interstitials. Then we will discuss impurities. Then line defects we will discuss, that is dislocations, mixed dislocations. Interstitial defects are also called as surface defects. And finally we will discuss the summary. No solid piece of material is a perfect crystal. Most solid objects are polycrystalline. They consist of numerous small single crystals or grains of random orientation. Note that grain boundary is a result of these grains of random orientation. We will be discussing throughout this course, and may be surprising at first, that lattice defects are responsible for many desirable properties of materials. Lattice defects are introduced to strengthen the metals, and defects are essential in the creation of semiconductor devices. With few exceptions, one can state that a perfect crystal is perfectly useless. To a greater extent, materials engineering consists of the introduction and management of the right defects. The arrangement of the atoms or ions in engineered materials contains imperfections or defects. These defects often have a profound effect on the properties of materials. In this session, we introduce the three basic types of imperfections: point defects, line defects, and surface defects or interfacial defects. These imperfections only represent defects in or deviation from the perfect or ideal atomic arrangement expected in a given crystal structure. The material is not considered defective from an application point of view. In many applications, the presence of such defects actually is useful. There are a few applications though where we will strive to minimize a particular type of defect. For example, defects known as dislocations are useful in increasing the strength of metals and alloys. However, in single crystal silicon used for manufacturing of computer chips, the presence of dislocations are highly undesirable. Often, the defects are created intentionally to produce a desired set of electronic, magnetic, optical, and mechanical properties. For example, pure iron is relatively soft. When we add a small amount of carbon, we create defects in the crystalline arrangement of iron and turn it into a plain carbon steel material, which exhibits considerably higher strength. Grain boundaries, regions between different grains of polycrystalline material, represent one type of defect that can control properties. For example, the new ceramic superconductors under certain conditions can conduct electricity without any electrical resistance. Material scientists and engineers have made long wires or tapes of such materials. They have also discovered that although the current flows quite well within the grains of polycrystalline superconductor, there is a considerable resistance to the flow of current from one grain onto another across the grain boundary. On the other hand, the presence of grain boundaries actually helps strengthen metallic materials. In later sessions, we will show how we can control the concentration of these defects through tailoring of composition or processing techniques. In this session, we explore the nature and effects of different types of defects. Point defects. Point defects are localized disruptions in otherwise perfect atomic or ionic arrangement in crystal structure. Even though we call them point defects, the disruption affects a region involving several of the surrounding atoms or ions. These imperfections may be introduced by movement of the atoms or ions when they gain energy by heating during processing of the material or by introduction of other atoms. The difference between an impurity and a dopant is as follows. Typically, impurities are elements or compounds that are present from raw materials or from processing. For example, silicon single crystal grown in quartz crucible contain oxygen as an impurity. Dopants, on the other hand, are elements or compounds that are deliberately added in known concentrations at specific locations in the microstructure with an intended beneficial effect on properties or processing. In general, the effect of impurities is deleterious, whereas the effect of dopants on properties of material is useful. Phosphorus and boron are examples of dopants that are added to silicon crystal to improve or alter electrical properties of pure silicon. So this is the schematic representation of different point defects in crystal. So first one is here is vacancy. Second one is an self-interstitial atom. Third one is an interstitial impurity. And fourth and fifth are nothing but substitutional type impurities. So fifth one is substitutional type impurity, whereas fourth one is an interstitial type impurity. Vacancies and self-interstitial. So this is the schematic representation of vacancies and self-interstitial. So this is the vacant site, so that's why we call is a vacancy. And here is a self-interstitial. The atom of this from the same metal, one atom is present or it has gained the position in between two atoms or in between the void. So that's why we call it as a self-interstitial atom. The simplest of the point defects is a vacancy or vacant site, one normally occupied but from which atom is missing. As you can see here, the atom is missing, so that's why we call it a vacant site, or it is also called as a vacancy. All crystalline solids contain vacancies, and in fact it is not possible to create such a material that is free of these defects. A self-interstitial is an atom from the crystal that is crowded into an interstitial site, a small void space that under ordinary circumstances is not occupied. This kind of defect is also shown in this particular figure. In metals, a self-interstitial introduces relatively large distortions in the surrounding lattice because the atom is substantially larger than the interstitial position in which it is situated. Means the size of this particular void is smaller than the size atomic radii of this particular atom. So that's why the surrounding atoms, they have to adjust themselves in order to occupy this new atom, self-interstitial atom. So that's why there is a distortion present in the local vicinity of this self-interstitial atom. The formation of this defect is not highly probable, and it exists in very small concentrations that are significantly lower than in comparison with the vacancy. The necessity of the existence of vacancies is explained using principles of thermodynamics. In essence, the presence of vacancies increases the entropy, that is randomness of the crystal structure, randomness of the crystal. So how often do vacancies jump? So you can see it here, the atom is present here, and in order to fill this vacancy, the atom has to jump from this position to this particular vacant position. So it requires some energy from this position, from move to this position to particular this position. So this energy we call as an activation energy called as a QV or EM. As you can see it here, so it's a vacant site. In order to fill this vacant site, the atom has to move from one position to vacant site. So it's a activation energy. So in order to atom to jump into vacant site, it needs to possess enough energy or thermal energy to squeeze through its neighbors. The energy necessary for motion is called activation energy for vacancy motion. The probability of such fluctuation or frequency of jump is called n prefix gamma, depends exponentially from temperature, and it can be described by using Arrhenius equation. The equilibrium number of vacancies n gamma for a given quantity of material depends on and on increases with temperature, and this is explained by using this Arrhenius equation. In this particular expression, n, capital N, is the total number of atomic sites, most commonly per cubic meter. Q prefix gamma is the energy required for the formation of vacancy, that is in joule per mole or electron volt per atom. T is the absolute temperature in kelvins, and K is the gas constant or Boltzmann constant. The value of K is 1.38 into 10 to the power minus 23 joule per atom K, or 8.62 into 10 to the power minus 5 electron volt per atom. Depending on the units of activation energy Q prefix gamma, the value of Boltzmann constant or gas constant has to be used. For most metals, the fraction of vacancies, so when we rearrange these terms and n prefix gamma divided by n, we call this particular term as fraction of vacancies. For most metals, the fraction of vacancies just below the melting temperature is on the order of 10 to the power minus 4. That is, one lattice site out of 10,000 will be empty. In order to understand the vacancies, equilibrium number of vacancies or concentration of vacancies, we will solve one simple problem. So the problem statement is here: calculate the equilibrium number of vacancies per cubic meter for copper at 1000 degrees centigrade. The energy for vacancy formation is 0.9 electron volt per atom. The atomic weight of copper, atomic weight and density for copper 63.5 gram per mole and 8.4 gram per cc respectively. So means atomic weight and density of copper is given to you, temperature is given to you, and vacancy formation, that is activation energy, is also given to you. So in order to solve this problem, first we need to calculate number of atomic sites per cubic meter for copper. That is capital N value we need to calculate, and this can be calculated by using this equation, that is Na into density divided by atomic weight of copper, where Na is nothing but Avogadro's number, that is 6.022 into 10 to the power 23 atoms, density 8.4 divided by atomic weight, you will get the total number of atomic sites per cubic meter for copper is 8 into 10 to the power 28 atoms per meter cube. You just substitute this value into this equation. 0.9 electron volt value is given to you. K is the temperature in kelvins, so convert this degree centigrade value into kelvins, and K is Boltzmann constant or gas constant, that is 8.62 into 10 to the power minus 5 electron volt per K. As activation energy value is given electron volt, so we will substitute 8.62 into 10 to the power minus 5 value instead of 1.38 into 10 to the power minus 23, and solve it. You will get the answer 2.2 into 10 to the power 25 vacancies per meter cube. Means that at 1000 degrees centigrade, in particularly copper, we have 2.2 into 10 to the power 25 vacancies per meter cube. If you rearrange the term, that is 2.2 into 10 to the power 25 divided by 8 into 10 to the power 28, you will get fraction of vacancies at this particular temperature. Next is impurities. There are foreign atoms in the material. Some impurities are undesirable and must be removed by purification. Silicon used to produce integrated circuits, for instance, can tolerate less than 1 impurity per 10 million silicon atoms. Other foreign atoms are introduced for their beneficial effects. Examples are the doping of semiconductors to make them N-type or P-type conductors. Impurities are also introduced to increase the electrical resistance and the mechanical strength of metals. Impurities are substitutional when they occupy a regular crystal site otherwise occupied by a host atom, or impurities may be interstitial when they fit in the interstitial sites between the host atoms. The addition of impurity atoms to a metal results in the formation of solid solution. Several terms relating to impurities and solid solution has to be mentioned. With regard to alloys, solute and solvent are terms that are commonly used. Solvent is the element or compound that is present in the greatest amount. On occasion, solvent atoms are also called host atoms. Solute is used to denote an element or compound present in a minor concentration. So this is this two-dimensional schematic representation of substitutional and interstitial impurity atoms. As you can see it here, in between the four atoms, small void is present and the solute atom is present in between these four atoms or void. It is occupied the space of void, so it is an interstitial impurity atom. Whereas in this particular substitutional impurity atom, you can see the foreign atom directly substitutes or directly replaces the solvent atom. So that's why we call it is a substitutional impurity atom. We will be discuss more about the solid solution in the strengthening mechanism topic.